start with the simplest possible case we can think of. Basic antenna array theory. Let's say we have two dipoles. They're separated by D. The origin in the center. And these are all fed like a standard dipole would be. Each individual element is omnidirectional and would put out to a particular location, each individually, field with magnitude E0. If we are in the far field, in other words, we're observing this system more than D squared, or in this case, the variable I'm using in this analysis is little d. So little d squared over lambda. I'm in the far field. These basic antennas basically radiate the same distance, so their amplitudes are going to be the same. It's in the same direction, although we're using omnidirectional antenna elements to illustrate this to start with. So that should produce the same, roughly the same E0 magnitude field. The only thing that will change is the phase between those two radiated elements. Because, depending on which angle I observe the system, there will be extra distance at a small scale traveled by one wave or the other. And the best way to geometrically see that is, let's look at overhead view. So the overhead view of this system, X, Y, have one element that is D over 2 above, and then one element over 2 below origin. And if I am over here at a distance R away, point of observation, R1 and R2 from an amplitude point of view are the same. But from a phase point of view, there's going to be an electromagnetically significant distance traveled here to here. In fact, if we evoke the far field approximation, where we measure distances for phase with parallel lines to my point of observation, what I really have is a distance R, and then the excess distance that this guy travels. Here, these dotted lines I've drawn are perpendicular to the parallel paths of my point of observation. Here's the origin, here's element 1, here's element 2. This guy travels an extra d sine phi, where of course phi is my azimuth angle. And if it travels an extra d sine phi, there should be a kd sine phi phase difference between the contribution at this point from this source and the contribution from this source. So let's go ahead and do the math for this to figure out what it is. My total field is going to be the superposition of whatever amplitude and phase would have arrived from a central element. I'll call the contribution of an imaginary central element dot. This guy here will be phase shifted exp plus j d over 2 k sine phi. And then superimposed on that will be this element down here, which will be shifted E naught exp minus j d over z k sine phi. Okay, so what I'm going to do, I'm going to factor the 2 out in an E complex field amplitude. And what I'm left with then is exp to the plus j d over 2 k sine phi plus exp minus j d over 2 k sine phi divided by 2. Probably see where I'm going with this because this is by Euler's law. Plus and minus complex exponential divided by 2 is really just the cosine of the argument. J over 2 sine phi. And of course, k, we remember, is 2 pi over lambda. So if I wanted to write this in terms of wavelengths, I have 2 dot cosine pi So even though the individual elements are radiating the exact same amplitude, and in this case they're starting out with the same phase, we'll learn about arrays that don't necessarily do that, I'm getting significant amplitude changes as I sweep my observation in phi, changing how I look at this system. It's interesting because that means I can take any arbitrary number of omnidirectional antenna elements, and by placing them at different points in space, I can make some radically directional or at least some really messed up looking antenna patterns. And what's more, E naught is really a function of the radiating element. I said, let's put one here and say what E naught is. I could have made a directional element, something that had a phi dependence, right? And when I go through and I do this analysis and I look at power, that's going to be proportional to 4 magnitude dot squared cosine squared of this exact same system. And what we see is that even with a generic pattern, even if this had a phi dependence, we see that there's a separability in the radiation of this system. By that I mean that the entire pattern here of the radiated system depends on what is often called the element pattern times the array factor. This term here in this system serves as the array factor. Something that is only a function of the geometry. So I can make all sorts of crazy patterns just by taking these omnidirectional elements and changing their geometry. I've only got 2 to work with at the moment, but we'll see this is generalizable in just a few. Or, I can drop in patch antennas or Yagi antennas. I can make an array of Yagi antennas. Those will add some directionality here. But if it's in the same place as my 2 elements, if I put 2 Yagis here, it will have the exact same array factor, and the total pattern is the multiplication of them. So just a hint of that at the beginning of the semester when we started to look at stacked dipoles of antennas. That was homework number 3, I think. That was a really nice exercise to work through because even before you knew what an array factor was, it seemed to be popping out of the math, right? I have a dipole pattern right here. And then over here is something that's a function of the number of elements that I stacked up in a row. So this is where this comes from. Let's go ahead and generalize this. Well, first let's talk about some special cases, just to show the amount of variety that come out of just this simple system. So the first case, what does the radiation pattern look like? Which shape does it have if I make D very, very small? How does case 1? Well, if D gets really small, then D is effectively 0 with respect to a wavelength. And my array factor here is going to be equal to zero. Oh, good. No feed dependence. That makes sense. If I basically take two elements that are omnidirectional, I put them right next to each other, that's a nice sanity check. That should just mean continued, constructive interference in every direction. Okay. Now, the second case, I want to put a little bit of generalization here, too. I'm going to take the source, and I'm going to add one more degree of freedom. I'm going to flip the source up. I'm going to drive these two elements. These are standard bent hanger symbol for antennas. But then I'm also going to allow something called a phase shifter. Some device that introduces arbitrary amount of phase shift in radius. Beta and one way to do that is just by adding an extra length of wire. And if you want an adjustable beta, you can just put different lengths of wire and put like a multi-pole switch to connect them. And you connect different lengths of wire if you want to digitally dial in different phase lengths. There are also analog phase shifters. You make them by usually with some sort of nonlinear material. At lower frequencies, you have to use magnetic material because you can basically change the mu by saturating DC bias or unsaturating the DC bias with an electromagnet. What does that do? Well, if the mu is small, then the wave travels more quickly through the medium at a high velocity of propagation. If the mu is big, if you haven't biased in the magnetic field on the substrate and it's part of a transmission line, then the wave experiences the full mu sub r and travels at a slow velocity of propagation through there. So for the same length, the same physical structure, it will experience different phase lengths through the device. And there's all sorts of variations on that idea. So anyway, let's just pretend we had one of those devices in the system. Now we've got two variables to play with. We've got the phase and we've got D. So in this case, beta is equal to 0. This is close together. Let's look at special case number 2. D can be whatever it wants to be, but beta is still equal to 0. And that is called broadside. And in that case, have our original expression. And there's still a dependence on D. If D is small, less than a wavelength, then what happens is that as I move these things apart, my beam starts shrinking, my beam width. My gain goes up a little bit, and my beam width shrinks a little bit. standard antenna principles, right? Just because these are arrays doesn't mean that the Fourier transform relationship between current distributions and patterns isn't satisfied. I take my currents and I push them apart, get a squinted up beam. Now, up until a point, I can play that game. If I start going more than a lambda, what happens is I start picking up sine lobes of this thing. So let's say I make a D that's 2 lambda. Okay? That means that I have 2 cosine pi lambda sine phi. My phi, as I go around in azimuth, is going to experience 2 cycles of sine, of cosine. So I've got a peak here, I'm going to go down, I'm going to pick up another peak up here, and then I've got symmetry in the problem. I get kind of a clover sheet shaped pattern. And these are side lobes. This was our main desired lobe, but it was actually small, and that kind of squinted up a little bit. Now I got side lobes that are increasing. And if I go to 3 lambda, I'm going to get another side lobe, and another one, and another one, before I have a really nice, pretty flower pattern. However, in broadside arrays, there's always a peak at phi, no matter how far apart I make them, how many elements I put in. If all of them are in a line and their phasing is 0, then I get broadside array. Case 3 is the one where we're going to make D equal to a quarter wavelength and beta equal to 90 degrees, so pi over 2 radii. What happens in that case? Well, my array factor, if I include the beta, is going to look like this. 2 times cosine, ID over lambda, sine phi, plus beta over 2. I've got a phase shift now between 1 and 2. Effectively rotate my pattern. Not a true rotation because it's inside the cosine. It shifts everything. This particular type of configuration shifts everything. Interestingly, let's go ahead and plug this in. If this is lambda over 2, beta is lambda over 2, I'm going to give lambda over pi over 4. But this is going to produce zero. I put 0 here and cosine pi over 4. That's cosine pi over 4 is what? 1 over square root of 2. Not the peak, it's not the 0, it's kind of in the middle. If I go all the way to positive 90 degrees, what's that going to give me? Sine of 90 degrees is 1, and this is going to be pi over 2. 3 pi over 4. If I go in the other direction, so I have negative 90 minus pi over. Look at my cosine. This point is at 2 pi over 2, 0. What I should have done here, what I should get, is something called an end fire.
The pilot field and sign, you can have the pilot field.
Oh, you're right. You're right. That's why it's not working out. Or one for the students. I don't know what was crazy about that. Okay, let me readjust my values. Thank you. Save the lecture. Pi over 4 plus pi over 4. I'll give you pi over 2. That's the case when phi is equal to. The pi over 2 case, then I've got pi over 4 plus pi over 2. Cosine of that is 0. Okay? So that means that if I were to graph this, draw out the path, you determine this part, it was 1 over the square root of 2. Up here, it would be 0 at phi equals to pi over 2. And then down here at phi equals to minus pi over 2, I get negative pi over 4. The sign of negative pi over 2 is negative 1. Negative pi over 4 plus positive pi over 4 is 0. Cosine of 0 is at a maximum. And then through symmetry, I can show that this kind of repeats. Oh, look, it's a heart. Or actually a cardioid. Like I have a lot of I have 3 young daughters at home they're all budding artists. And so this is a heart. This is a cardioid. Cardioid, of course, coming from the Latin for heart. Okay. And that's called end fire. If I wanted to switch the degree of the end fire, so the end fire array is one that I've phased in such a way that it actually puts a maximum along the z-axis. In this case, the negative z-axis. If I flip the phase, I can turn it around and make it go the other way. That's interesting. You just take 2 elements by just changing the phase. What used to be dipole-looking pattern that kind of had a maximum in that phi equals 0 direction now points over here. Or if I flip the phase, it points over here. So now we actually see the beginnings of the idea of a dynamic array, an antenna array that can be electronically adjusted and steered anywhere in the environment. Here. Oh, that's end fire, which is 0 degrees. Over here, 90 degrees. Positive 90 degrees over here. I want to get something off axis and put my peak gain in that direction, then I just need to dial in something between those values using this transformation, this mathematical transformation, the array factor. And then I can do that with arrays of all sizes. The devil's in the details, though, because you got to have phases that are properly connected. You got to have phase networks that are low loss, which is really hard to do, especially at higher frequencies. You have to know how to map the desired phase to what you're trying to get on the outcome. One other thing to mention about this is that lambda over 4, although technically it will work, I'm starting to get elements that are very, very close to one another. And there's one non-ideal phenomenon that I have not told you about in antenna engineering called coupling. At least I don't think I have. Coupling, but you have actually experienced it already. It's basically how a Yagi-Uda array works. If you bring 2 antenna elements close enough so that they are within the quasi-static field of one another, basically within about a wavelength, length over 2, depending on how strict you are about defining that quantity, where the quasi-static field begins. If you bring those antennas that close, then you'll excite parasitic currents. One will excite parasitic currents on the other, and you will no longer have the desired excitation that you think you have. You actually get some directionality, just like a Yagi. You thought these were two antenna elements that had omnidirectional patterns. In the presence of one, it might throw the beam in one direction or the other. And so generally speaking, we don't like to put antenna elements any closer than lambda over 4. Another thing of this from a receive point of view is if I have two antenna elements and I'm bringing them close together, remember we said there's an effective electromagnetic aperture around those antennas that gather field strength from a wave and absorb it and carry it to the transmission line both it's connected. If those effective electromagnetic areas start to overlap, then that antenna is stealing some of this guy's power that he would have normally used to pull in and excite his load, and vice versa. And that will do crazy things with the pattern of the individual elements, as well as the collective system they're being used as an array. So lambda over 4 is uncomfortably close, but we still do it to get to things like n. Lambda over 2 is a little bit better. That's nice. The electromagnetic apertures don't really overlap, and you can approximate everything as non-coupling. Yeah.
You said that was parasitic.
Parasitic capacitance and inductance. It depends on the configuration. If it's two dipole antennas, it tends to be more capacitance than inductance. If it tends to be two loops that are close together, it's more inductance. But there's a little bit, you can be guaranteed there's a good bit of both at high frequencies. They're close. Okay. Time for one more thing. Only type of array that you're going to need to know about in this class is something called the uniform linear array. Probably the most common way to implement them. See them in everything from base station antennas to radar antennas. And here we have multiple elements in my uniform linear array. So here I'm going to have 1, 2, 3, n elements in my array, much like I had 2 elements in my first example. And each of those vector position, r sub 1, r sub 2, r sub 3, all the way down to r sub n. R is a vector that has the position of each element. And what you can show, in general, the array factor, this antenna, as a function of phi and theta, is going to be equal to n is 1, a sub I, which is the amplitude rating, theta sub I, which is going to be the phase factor for the ith element, and the position, r sub I, And this is what the array factor for that system would be. Now, there are a couple things in here we haven't introduced yet. First of all, this is a general expression. I can put those anywhere in three-dimensional space. And because r hat, recall, is the unit vector that points in the direction of my point of observation, hopefully in the r-far field. Let's move first. Remember, in cylindrical coordinates, that's going to be cosine, sine theta, cosine phi, stick it on the x, sine theta, sine phi, stick it on the y hat, plus cosine theta. So we say all of our orientation dependencies are actually wrapped up in here. We put a wavelength 2 pi over lambda, the positions of all of our arrays, the phase shifts that we want to introduce to all these different elements. And then the weighting, we haven't talked about a weighting yet, but there's nothing that says I can't build an array where I only put half the amplitude in one element that I put in the other. So maybe a sub 1 would be 1, a sub 2 would be 1/2, and maybe a sub 3 would be 1/3. So why would you want to do that? Well, it makes the pattern different. It's another way to control the pattern. You don't see that done too often, although it is popular to do with arrays that have very, very small side lobes. How you get small side lobes. Make a nice uniform linear array, and then at the end you start tapering. You're making smaller and smaller amplitudes, not just playing with the phase. It gives you an extra degree of freedom to kind of smash down those side lobes. You never get them to 0, but you can get them really far down on your array properly. So the linear array is really this general case. This is the expression you can use in the array factor of any arbitrary geometry. But the linear array has uniform part. There are two things that are uniform. It's equally spaced, actually three things, equally spaced. So in a line with spacing. So in a uniform linear array, all of these R's, unlike this general expression, are in a line, they're d units apart. That's the first uniform and linear thing about them. Spacing is uniform, and it's in a line. That's why we call it a linear. We also hope that it's electrically linear, in that by double the voltage, I get field strength. If I don't get that situation, I have a nonlinear nightmare channel. Anything nonlinear. So equally spaced in line. The other thing is that amplitudes are all equal. I am exciting this uniformly with the same magnitude source. So that's my uniform. That's uniform as well. The last uniform thing is that my phase taper is also linear. So that b sub I plus 1 minus b sub I, the phase difference between successive elements in my uniform linear array, constant. In other words, these two are beta apart. These two are beta apart in phase, which means these two are 2 beta apart. This is 3 beta apart from the first one, which is beta from this one, 2 beta from that one, so forth on down the line. If that's the case, let me put the final expression. I don't have time to prove it mathematically on the board because we're about ready to break. Don't get too disappointed. You can do this with a simple geometric summation applied to this with simplifications in the privacy of your own dorm room. My amplitude factor for the uniform linear array, I can always put this form. Sine squared n psi over 2 divided by sine squared psi over 2, where psi is the helper variable kd sine phi plus beta. This is the key result that I want you to take home. Very simple geometrical term for figuring out what the pattern is for the uniform linear. You just need to know distance with respect to a wavelength, the separation distance between elements, the phase separation between elements, what angle am I observing it at? I have this. I mean, it's deceptively simple. You have to be careful, too, because at some point you're going to get nulls. Whenever you get a null here in this expression, because there's an n integer multiplying the argument of the sign in this one, there's also a null here. So you have to use L'Hopital's rule to actually evaluate it at certain discrete points around the pattern. But this will basically show how you can change D and beta, get main lobes as well as side lobes that dance around. So when we come back on Monday, we'll talk about a special type of uniform linear array. We'll concentrate on the end-fire array, how to make an array of antennas that shoots in one direction or the other direction. There are some tricks to designing those. There are different types of end-fire arrays. One of them is a Hansen and Woodward end-fire array, which is how you maximize directivity and minimize beam width in a particular direction. That's nice. And then we'll talk about helical antennas, which winds up being really just a bunch of winding, electrically large helixes, just like a coil, one strand of a DNA. But what's really neat about that is that you can model it as an array of loop antennas, uniform linear array, that just happens to have Hansen and Woodward end-fire phase shifting between the elements. You get this beautifully directed antenna. It also happens to be really broad band because there's this kind of weird traveling wave correction factor in it that gives it almost 2-to-1 bandwidth, which is really cool too. I'll bring some examples in if you haven't seen them already in the laboratory, because I think one of your experiments involves helical antenna. Okay, let's break. I've talked long enough.